Alright, in this video we are going to do a couple things. Look at how you can show enthalpy reactions in three different ways. And then we'll look at some enthalpy reactions and try and solve for a heat of reaction using heats of formation. Okay, so those are the two things we'll do in this video. Okay, so to begin with, showing enthalpy reactions in three different ways. So three different ways you can do it. One way, and the first two are very similar, but what we do instead of just saying what the heat of reaction is, we include that heat of reaction on one side or the other side of the arrow. So in this side here, it's on the product side, so it's something that's being produced, and if energy is being produced, then it's an exothermic reaction. So any exothermic reaction you would write, if you have an amount of energy, a heat of that particular reaction, you would write that on the right-hand side. Another way you can write it is just write the reaction out normal and then say, hey, the change in heat for that particular reaction or the heat of reaction is this. Notice they have a negative there. That indicates an exothermic reaction. The last way you can do it is using an enthalpy diagram, and it's basically just saying how much energy you start with and how much energy do you end with. So this one, these reactants here started at a high energy level and they wound up at a low energy level, so that you can't lose any energy, can't be created or destroyed, that kind of thing. It must be given off somehow, and it's given off as energy. It could be given off as heat, but we could take that, maybe that energy, and store it somehow. So this is another example. So from high to low is an exothermic reaction. Heat is given off to be used somewhere. Endothermic reaction is very simple, but just opposite, right? So if you have an endothermic reaction, that's one where you have to input heat or input energy. And in this case here, if I take carbon dioxide and water, if I input this much energy, then typically plants get that from the sun. So if we input that amount of energy, then it produces glucose and oxygen. Okay, so if energy is written on the left side, endothermic. Also, if you just write the reaction as normal and you write your heat of reaction off to the side, endothermic reactions are always written with a positive value. Similarly, in an enthalpy diagram, the reactant start at a certain energy level, energy is added into that reaction, and so the products wind up to be at a higher energy level. Okay, so that's three ways you can write enthalpy diagrams. Okay, so sometimes for a chemical reaction like this one, this is photosynthesis, we know what the amount of energy for that particular reaction is, and sometimes we don't. If we don't, then we can use something called heats of formation to figure that out. So, if you need to determine the heat of reaction, if you don't know if it's not on a table or something, you can actually use the molar heats of formation from a table in your data booklet. And at the top it says standard molar enthalpies of formation at a specific temperature. So you can use those heats of formation to figure out what the entire heat of reaction is. Basically what you're doing is, if you have a chemical reaction, like that one we had on the last page, CO2 plus water, yielding glucose, that's a 6, plus oxygen. So if I wanted to know what this heat of reaction is, what I can do is I can just figure out what the heat of formation for this one is, heat of formation for that one is, for glucose and for oxygen, and then once I have that, I can just subtract them to see which one's higher. Not really to see which one's higher, I just subtract them to figure out what the heat of reaction for that particular one is. Here's the formula. So to figure out the heat of reaction for any reaction, this symbol here means add up. So add up all the products, add up all the reactants, and subtract them. Okay, so let's try a couple of quizzes where we do that. I guess maybe I should give you some rules first. So here's some rules. First, write a balanced chemical equation, including states, because some compounds have different heats of formation depending on their state. write the formula. That's that delta H equals add up things, that one. And then plug in your molar heats of formation for each compound. So do the ones for products, do the ones for the reactants, then we'll subtract them. Now, a couple rules as you go is any element by themselves, like oxygen or iron, if something's all by itself, then the molar heat of formation for that is 0. Okay. Also, when you're doing all this adding up, you have to multiply the heats of formation by whatever their coefficient is in the balanced chemical equation. I'll show you how to do that. And then solve the equation. That's this guy. Add up the products minus add up the reactants. And then lastly, if you are wanting to get a molar heat of formation, or not formation, molar heat of reaction, then you'll divide whatever your total is, this thing, by however many moles there are of the substance that you're looking for the molar heat of reaction by. I'll do a couple questions so you sort of can see that. Right, so here's a question. Sodium hydroxide neutralized with hydrochloric acid, what's the heat of reaction? Okay, so, and we've done this reaction, sodium hydroxide and hydrochloric acid. So, sodium hydroxide, we'll say it's a solid just because this one over here is a solid. Reacts with hydrochloric acid. Again, over here, hydrochloric acid, they just have it written as a gas. I'm going to assume that it's the same, but I'll write a gas here. Okay, it reacts to form. It's a double replacement reaction, so it'll be sodium chloride. Do I have that one written? Yeah, as a solid plus water. And water we'll say is a liquid. Okay, so that's the reaction. I'm a little bit worried about this because I do have this one as a solid, and we can do that, solid sodium hydroxide, but then hydrogen chloride or hydrochloric acid, typically we write that as aqueous, but I don't have aqueous on my standard heats of formation chart, so I'm just going to go with this one. Alright, so there's my chemical reaction. See if it's balanced. 1 sodium, 1 sodium, 1 chlorine, 1 chlorine, 2 hydrogens, 1, yep, balanced. Okay, so then it says to write down the heats of formation underneath each one of those. So sodium hydroxide, it is negative 425.6. Hydrogen chloride, negative 92.3. Sodium chloride over on this side, negative 411.2. And water as a liquid, notice that water's got a liquid and a vapor, is negative 285.8. So if I want to know what the heat of reaction is, I'm going to have to add up all of the products, add up all of the reactants, subtract them. So here's my formula right there. So it's equal to the products. I'm going to put them in brackets. So negative 411.2 plus a negative 285.8. Those are my products. Minus bracket negative 425.6 plus a negative 92.3. Now, notice there's one step on the thing before that's set to multiply the heats of formation by whatever their coefficients are. In this case here, they're all 1. So I didn't need to multiply these numbers by any number because they're all 1. Now, I would just take and I would plug this on my calculator, just as it is. So, bracket, negative 411.2 plus negative 285.8 bracket minus bracket negative 425.6 plus a negative 92.3 bracket go. So in my question here, it's negative 179.1 kilojoules. All of these numbers are kilojoules for reaction. They're actually kilojoules per mole. I guess I can write that, kilojoules per mole for each one of them. And so, but since I multiplied down here, I didn't because there was 1 mole, but all of these would just be kilojoules. Okay, so that's how many kilojoules of energy for this particular reaction. Now, if there was a number other than 1 here, what I would say is the molar heat of reaction would be negative 179.1 kilojoules divided by whatever that number is there. Since it's a 1 this time, the heat of reaction, molar heat of reaction for this one is the same as the heat of reaction, or negative 179.1 kilojoules per mole. Let's try another one. Hopefully this next one we have to balance the equation. Oh yeah, we will. Propane burns. Determine the molar heat of reaction. Oh, molar heat of reaction for propane. Okay, so propane. Propane is C3H8. Okay, and we'll say it's a gas plus oxygen as a gas produces carbon dioxide as a gas plus probably water vapor, so as a gas. All right, there's my chemical reaction. Let's balance it. I think I need a 3 there, probably a 4 there. So that gives me 6 plus 4, that's 10 oxygen, so I need a 5 there. Okay, now let's write the molar heats of formation down for each one of those. I've just grabbed them from the chart. That's where I got these from. So for propane, it's negative 103.8 kilojoules. Oxygen is an element, so it's 0. Carbon dioxide, negative 393.5 kilojoules. And water, or it's kilojoules per mole. And water vapor, negative 241.8 kilojoules per mole. Good. Okay, so now down to my formula here, heat of reactions, add up the products. Okay, so bracket. I only need 1 propane. Oh, I got to start on the product side. So there's 3 moles of carbon dioxide. So I'm going to go 3 moles times negative 393.5 kilojoules per mole. So the moles cancel out. Plus 4 waters. So it's negative 241.8 kilojoules per mole. You see the same thing is going to happen. So this would be kilojoules. Okay, so that's the products. Minus, now we'll do the reactants. So it's 1 mole times propane. So there's just one of them. So I'll just write negative 103.8 kilojoules. Plus the it's 0. Oxygen 0. Okay, so now I can just plug this into my calculator. If you want to multiply that through and this through first to come up with a number, you can. But as long as you're pretty good with your calculator, putting brackets in where you should be all right. So I've got 3, or bracket, then 3 times negative 393.5, okay, plus 4 times negative 241.8, bracket, minus, bracket, negative 103.8 plus 0. Okay, go. All right, so in this one, I came up with negative 2,043.9, and this would be kilojoules, because all these would have been moles, and this is kilojoules per mole, so all the moles got canceled out. So this is kilojoules of energy. So the heat of reaction for this is negative 2,043.9 kilojoules. Now, if they want to know the molar heat of reaction, then I'll take that 243.9 kilojoules and divide it by whatever's in front of propane. And that's, if they ask for determine the molar heat of propane, that's what you would use. So divided by 1, of course it's going to be the same number, negative 2,043.9 kilojoules per mole. Now, one thing with sig figs rules apply. And so if I have, it looks like I have 4 sig figs everywhere. So in my answer, I should only give 4 sig figs. So it'd be negative 2,044 kilojoules per mole. Okay, hopefully you're getting the idea of these. Let's just do one more. One sort of changes things a little bit, but similar. Okay, combustion of phenol represented by the equation below. And this time they give us the heat of reaction. So they say the heat of reaction is negative 3,059 kilojoules per mole. I guess that's a molar heat of reaction, or molar heat of combustion. That's what the comb there stands for. And they want to know, calculate the heat of formation for phenol. So this one they don't know. Let me just see in my data booklet. Oh, I don't have phenol there. Darn. Okay, so they want to know that one. Okay, so I can use the same formula. It's just I'll have to rework things a little bit. So that's the one I don't know. Oxygen I know is 0. Carbon dioxide, negative 393.5. And there's 6 of them, so I'd have to times that by 6. And I have 3 water gas. That's the 241.81. Negative. Okay, so my formula down here, the heat of reaction is here. So that's negative 3059 is equal to, add up the products. So that's 6 times negative 393.5 plus 3 times negative 241.8 minus the reactants. Oh, I don't know them. If I'm adding 0, I don't have to worry about that. But here I don't know this one. Let's call it x. Okay, so now to solve, I'll move x to the other side and make it positive. Negative 393.5 plus 3 times 241.8. And I'm going to move this one to the other side. If it's negative on this side, moves it to the other side, it becomes positive. Okay, now I plug it in my calculator. Okay, so I need to go bracket 6 times negative 393.5 plus 3 times negative 241.8 bracket plus 3059 go. So x is equal to negative 27.4 kilojoules. So that will be what this one is. Since there's only 1 mole there, it'd be kilojoules per mole. If that was a different number, I might have to change that. Okay, hopefully that helps you with finding heats of reaction given heats of formation for reaction. And also at the start we looked at 3 ways of representing heat's energy in heat of reaction. Okay, hopefully that helps.